So we're starting off this conversation with, I mean, it's kind of a joke, but it gets at a bigger point. So everyone understands that, the lady who's modeling the shirt or whatever isn't the kind of model we use in physics. Great. We know that's not a model that we would use in science. Everybody understands that a globe is a model. Everybody understands that a model airplane is a model. A model of a spaceship is a model. Physical models are well understood. What people struggle with a lot more is the idea that that's a model too. That's a visual model. Does anybody know what this is? Okay, it's a circuit diagram, yes. Every now and then I get somebody who's building their own circuits at home, but it's rare. That's a circuit diagram. And if you understand how to read it, that models for you what is happening inside a piece of electronics hardware. This one, years ago, I read a book by this sort of preeminent climate scientist, and he talked about having an undergraduate come up to him who was so excited because, this guy had been, a Nobel nominee. His work was very well known. And this undergrad was so excited to be working with him. He said, do you think you could show me the climate model? Because he was assuming that it was a physical model like this. We all get that that's a model. It's not. It's a bunch of numbers in a computer program somewhere, and when you put this in, all these change. And when you put this in, all these change. That's a model too. And computer models are widely used. This is output, actually, from a computer model of climate. So, that's a model. That's a model. What about that? Looks like an equation. Yeah, it's a mathematical model. When you put in one value, you generate a series of other values. Now, this is a rather more complicated equation than anything that we're going to use in high school physics 1. We don't go there. Thank your lucky stars and mine too, because I think we'd all tear our hair out. We can have a relatively simple mathematical model. F equals ma is a way to mathematically model the acceleration that an object will achieve with a given amount of force. It's an equation, yes. It's a mathematical model too. We can predict and project the amount of acceleration that the object is going to achieve with a given force, and then we can apply that force and compare our results to the model, to the answer that the model generated. That's the use of a mathematical model. So, that's a model too. Physical models are the part that are well understood. Visual models, very often people, well, no, that's just a picture. Yeah, it's a visual model. A model is a representation of reality. Now, is the model perfect? Never. No model is perfect. Okay, so models come in under experimental design. So we talked a little bit when we last left our physics heroes way back last week about the scientific method and how it applies in chemistry. So, we said there are actually, there's more than one method. It's not a single cookbook flowchart approach. When we are designing ways to test hypotheses, we very often use models. So, okay, let's use F equals ma because it's something that you did in physical science. It's very simple. It's a 3-part equation, but it models our understanding of the relationship between mass and acceleration and force. So, if we wanted to test that understanding, we take an object of known mass, we apply a known force to it. Do we get the acceleration that is predicted by the model? If we do, then we can say that, yeah, our model is pretty good. We are doing experimental design that tests a mathematical model. We can do experimental design that tests a physical model too. We can build, who here has watched Mythbusters? Darn it, I should have brought clips. Okay. Mythbusters, I don't know if they ran this in Mexico. It was dubbed in a bunch of languages, I know. Here, we're gonna do a clip. So in that episode of Mythbusters, which I should have grabbed a screenshot from, they created a physical model that tested the hypothesis, which was their myth, that the unwinding coil of rope could pull you over. Verbal models are literally just verbal explanations. of how a phenomena works. And visual models we all understand pretty well. A map, a circuit diagram, those are visual models that show how things are related in physical space. Now, let's talk about maps. Are they perfect? No, they're not. The most famous sort of disequity perpetuated by maps, because of who the first map makers, who the map makers were whose maps we use in the modern world. Europe looks a whole lot bigger than it is, and Africa looks a whole lot smaller than it is. And you can't make all the continental masses scale correctly on a flat piece of paper. You just can't do it. So you sacrifice accuracy to get them all in there. Now, that's a visual representation, but is it perfect? Of course not. It doesn't represent every aspect of reality. It doesn't represent every speck of anything. Models are very seldom perfect. That's just one of the sort of assumed weaknesses of using any kind of model, is that there are going to be imperfections. Models cannot represent every single piece of reality. They can't represent all the relationships. The more complex they are, the better that they can do that. But by the time you get something that's so complex, it's hard to use. So we tend to simplify the world to put it into a model. Thought experiments and controlled experiments. We're going to talk about the controlled experiments, and then thought experiments I'm going to leave to my Norwegian, Icelandic, Danish. You'll meet him in a minute, my friend. Controlled experiments are the ones that you're all familiar with. You did a STEM fair project for Ms. Berger as a sophomore, and that was right before everything shut down. Did you guys finish STEM fair projects? I know, Juan, you did not in here. You may have in your home school. Controlled experiments are what we're most familiar with in terms of experimental design, where you have a control group that doesn't get whatever the treatment is. You have an experimental group that does. You know the joke about the biologist who had twins, right? Her first words were, "Oh, good, I have a control." Not that a biologist would ever do that, of course. Sure they would. But anyway, controlled experiments are the ones that, like I said, we're most familiar with. So, with that, oh no, it doesn't work that way. Let's go to our quick little video that'll give you a better idea of thought experiments. So we looked at the video on models, on thought experiments. Controlled experiments, of course, are the ones that you should be most familiar with. That's where we have a control group and an experimental group. One gets the treatment, one doesn't. Questions, thoughts, comments? Okay. Okay, so we'll go to your recall quiz over branches of physics, scientific method, and models.